Hello, I'm Alia Saad. On behalf of my team, I thank you for joining the presentation on our work titled PrivacyScout Assessing Vulnerability to Shoulder Surfing on Mobile Devices. Previous work showed that shoulder surfing, the act of observing content shown on device screen without users' consent, has a serious impact on users' privacy, security, and even safety. Consequently, a large body of research has investigated means to understand and mitigate this event. In this work, we present PrivacyScout, a novel method that predicts shoulder surfing risk based on the visual features extracted from the observer's face as captured by the front-facing camera. To that end, we considered in our study design two independent variables: the shoulder surfer's location relative to the phone and the content type. To overcome the limited field of view of the front-facing camera in most of the market available smartphones, we attached a wide-angle camera. With this attachment, both cameras had an identical angle. Starting with the observer's location, as seen here, we placed the phone on a table simulating the height of a phone in use of a sitting user. We specified four distances, 50, 100, 50, and 200 centimeters from the phone, and three angles on the y-axis: 0, front-facing, 30, and 60 degrees, resulting in 12 different locations. We used a rotating prototype to control the y-axis rotation of the phone. Regarding the content, we selected the sensitive content types that are reported to be shoulder surfed according to a previous survey. The first content type is the pins. We recorded 12 different videos of pin entry with no repeated digits. We selected 12 texts from an available dataset similar to the font of a messaging application. Finally, 12 photos were also selected from an available dataset, all contained between 2 and 4 people. The participants or the observer were only asked to move between the 4 different points, and the order of locations was counterbalanced using a Latin square design. The content and the angle of the phone was controlled by the experimenter. 16 people voluntarily participated in our study, 15 males and 1 female. Age ranged between 22 and 34, and height between 169 and 202 centimeters. All participants had a normal or corrected to normal vision. The contributions of our work are twofold. First, we present the first detailed analysis on the success of shoulder surfing beyond user authentication against commonly attacked content types: pin, photo, and text on mobile devices. Our fine-grained analyses for distances versus 3 observation angles are based on a 16-participant user study and simulated shoulder surfing attacks in a lab, which is in line with other shoulder surfing studies. Second, we present PrivacyScout, a novel computational method that leverages visual features extracted from an image of the potential attacker to then regress a score that represents the shoulder surfing risk. Let's have a look at the first contribution. We discuss our results for the different types that we analyzed, starting with the pins. In the pin condition, study participants that played the role of an attacker were asked to reproduce the pin that was shown on the screen at different distances and viewing angles. We then used the edit distance or Levenshtein distance to compare the actual ground truth pin and the one observed by the study participants. It's a distance metric between 2 input strings that associates a cost to a single character edit: insertion, deletion, substitutions, and also transposition. As such, the edit distance is a metric that indicates how close the pin observed by the attacker is to the actual one. A score of 0 indicates that the 2 pins are identical, while a score of 4, the pin's length, means the attacker cannot observe any of the digits. Our main finding is that pins are vulnerable independent of distance or observation angles. Our analysis did not reveal any statistically significant results, neither of the main effects of distance or angle or interaction. To assess the vulnerability of photos during shoulder surfing attacks on mobile devices, we calculated 5 different evaluation metrics: success rate, indoors versus outdoors, success rate of correctly counting people in the photo, success rate of recognizing the facial expressions in the photo, and the success rate of fully or partially recognizing the activity in the photo. There was no incentive to lie, as there was no compensation or reward to do so. Using a two-way repeated measures ANOVA, we found that the influence of distance on success rate facial expressions and success rate activity was statistically significant. The angle played a significant role on success rate count people and success rate facial expressions. Looking at the interaction effects between distance and angle, we did not find any statistically significant influence. We assessed the vulnerability to shoulder surfing of textual content on mobile devices using 4 evaluation metrics: success rate recognize words, success rate understand context, success rate retrieve names, and partial success rate retrieve names. These were our main findings from our studies. For detailed analyses and additional results, please refer to our paper. Our second contribution is PrivacyScout, a novel computational method that leverages visual features extracted from an image of the potential attacker to then regress a score that represents the shoulder surfing risk. We used the same images from our data collection study, in which we collected images of the attackers using 2 devices, a mobile phone and a GoPro with a wide-angle camera. Here is an example of the collected images. What does our PrivacyScout actually do? Using different combinations of the image features we mentioned, we train support vector regressors to regress a shoulder surfing risk assessment score. We did this for the 2 conditions that we saw the distance and angle played a significant role, for the photos and textual content. However, given the time constraint, I will only cover one example, which is the photos. Based on the data from our user study, we derive each score as a sum of the individual characteristics for each content. For instance, for the photos, the score is calculated as the success rate indoors versus outdoors, the success rate of counting people, the success rate of recognizing the facial expressions, and the success rate of recognizing the activities. So how well does such a model work? We evaluated our models and reported the mean absolute error, which is commonly used in regression tasks. All the evaluation results are from leave one subject out cross-validation. Concretely, we report results for one of the 2 use cases, the photos. We compared our method with 3 naive baselines. The naive constant is a method that would always report a high shoulder surfing risk if a second face is detected using the front-facing camera. As seen from the evaluation results, any method, either ones that use more complex feature sets, like using all features, or even simple ones that only use the face position in the image, can predict the shoulder surfing risk more accurately. Note that some of these feature sets have very different computational requirements. For instance, face detection can be performed on many current smartphones in real time. However, estimating the user's gaze direction requires more complex models or neural networks that may not run on current devices in real time. While our work is the first to assess the shoulder surfing risk based on visual features extracted from the observer's face as captured by the front-facing camera in combination with the content, it also has several limitations. First, our method is only as good as the underlying face detection algorithm. If no face can be detected, our method cannot be used to predict the shoulder surfing risk. While most of the current generation devices have limited field of view, wide-angle cameras are much more promising as they capture the user's surrounding better. Moreover, there are already smartphones that have a wide-angle front-facing camera. Second, another limitation may be due to the difficulty of acquiring a diverse training set for our method. For PrivacyScout to generalize, it needs a wide range of observation and viewing angles. The results that we saw earlier used images from our user study, 4 distances by 3 angles. However, in real world, some of these images cannot be used as the user may occlude the shoulder surfer. For instance, when the shoulder surfer is standing behind the user. As such, future work should investigate how many images and from which angles and distances are necessary to make our approach more robust. As a take-home message, we introduced a novel approach to analyze the impact of distance and angle on the success of shoulder surfing attacks. Our findings show that while pins are vulnerable independent of the locations, distances and angles played a role for photos and text. Based on the earlier findings, we could regress a shoulder surfing risk score. Thank you for watching.